I have written here what we have discussed in the last class, and the main thing that we have discussed is on the Laplace transform of e to the power at, which is going to be very useful because we are going to see what is the meaning of the shifting theorem. Either you can call by the name shifting theorem or by the name translation theorem. Translation means like this, moving. Okay, so you can either move the vertical axis to the right side or to the left side, so it is called translation. It's also called shifting. Scaling means you can make it to grow, or you can make it shrink. Okay, zoom in, zoom out. But that is scaling. Scaling is another property. So we will see what is the shifting property in today's class, and consequently we can solve some of the problems very easily. And then the shifting comes mainly because of the e to the power of at, and that is why we have started the problem solving starting with e to the power of at, because e power at is the main function that is going to be very useful to develop the problem solving techniques. After finishing the shifting, we will see if possible the scaling later. So now what we have done, so that means we are going to start here. We have already done the discussion on the Laplace transformation of e to the power of at, and I am going to explain what is the connection between this and the translation property. So that's what I am writing down here. So what you understand here is that every time we write down like this, the function f of t is given to you, right? So you have the function given to you, you take the Laplace transform, we get the result as capital F of s. And we have this usual tradition that small letter will represent the function before doing the Laplace transformation, and capital letter will be used for the function after Laplace transformation. So this is the convention that we are going to follow. This is very important, that we have to maintain a particular convention. If you keep on changing the convention, then it will be a total chaos for understanding. So you see a capital letter here after doing the transformation, and you see a small letter f here before doing the transformation. In some of the textbooks they do the other way, okay, so which will add confusion if you start reading multiple books at a time. So we follow the same convention, that capital F will be used after the transformation. And now the main result that you got for the Laplace transform of e to the power of at is that it is 1 divided by s minus a. Of course, I am not going to repeat the region of convergence, where you understood how to write down the region of convergence for that. The main result is that the Laplace transformation of an exponential function is nothing but 1 over s minus a. This a, what is happening here, is exactly this a that you have here. So therefore what happens is that our final result, we will be writing like this, that the final result is always a capital F of s. Capital F of s means we got the result of doing Laplace transformation. So this is f of s. So just for information, I would like to write down here, suppose if I say that there is a function x square. X square is a function that you have. Suppose if I say that x square is a function of x. X square is a function of x. Do you agree? Then you say that yes, you agree for that. The next question that we are going to ask is that, suppose if I have x minus 2 whole square. This is another expression. Do you agree that this is also another function? I am not saying same function. This is also another function. Okay. Let me make it clear that this is a different function when compared to the earlier one. Do you agree that this is a function of x? X minus 2 whole square. Again, you agree that this is a function of x. Now we are asking another question. The same x minus 2 whole square is there. Do you agree that this is a function of x minus 2? So this is a function. So do you agree that this is a function of x minus 2? So the difference is that earlier we were asking whether it is, let us keep the name changing, h of x like that. So do you agree that x minus 2 whole square is a function of x? You said yes. Now we are asking, do you agree that the same function is a function of x minus 2? You also say yes. Okay. This is not translated. This is h here, this is g here. So they are all different names, so there is no confusion. So which means that this function can be, we can understand this as a function of x here, or we can also understand that this can be rewritten as another function of x minus 2. This when you write like this, we say that something is shifting, or we say that translated. That means x is translated by an amount 2 units to the right side. That's how you understand. So both of them are tick here, but right hand side is same. So it is up to you whether you want to consider this as a function of x or it's a function of x minus 2. So that is the place where the idea of shifting comes, and it all comes from the Laplace transformation of e to the power at. So that is an idea. Keep this idea that you have, and then we can now see here, we are asking the question, what is this s minus a here? This 1 divided by s minus a is a function of s. You therefore ask whether this is a function of s minus a or not. This is also a function of s minus a. So it is up to you whether you consider this way or that way. So therefore, rather than saying it is a function of s, we will now say that this is a function of s minus a. So now I have written like that. A function of s minus a is given by 1 divided by s minus a. If you understand like this, then we can say that s is shifted by a. S is shifted to s minus a. So this is the basics, or we say that basic idea of the shifting, what is going on there. So whenever you look at what is the conclusion that I would like to tell is, whenever you look at e to the power of some constant time t in the problem solving, then you immediately remember that some kind of translation is happening in the s variable. In the s variable, okay, not the t variable. Okay, t variable nothing will happen. S variable only, it is shifted because it is a function of s minus a. So our conclusion is f of s minus a. And this a, where from it comes? This a comes from e to the power of at. So actually that's the a that you have here. So that a is exactly coming over there. So in case if I am going to do for e to the power of I omega t like that, then you have to write down that this will be converted like this, f of s minus, you put this I omega here. So in this way you can do the calculation for the shifting, and then you can ask the question, what happens if there is a minus originally here? If there is a minus originally, you put a plus here. So if there is a minus here, you put the plus there. So this is all about the shifting, and we will see how it works by doing this calculation. So I would like to erase this, and then we will start with the. So the original statement is Laplace transform of f of t is capital F of s. So now we are asking the question, what happens if you multiply by e to the power at? That's all. This is what we are asking, and let us try to do the integration directly, which will give you the answer. So since most of the steps you are familiar, if you have seen the last 2 videos, then we can quickly proceed here. So we can write like this. It is the integral 0 to infinity e to the power at. Then you can write this f of t multiplied by st, then dt. So which can be written down like this. These two you combine, then you have this f of t. Like this you have. Now what you do is, almost the problem is solved. Okay, and that's all. This is the answer. But just for understanding, what happens if you are going to write down s minus a as a new variable s prime? Because there is an s minus a there. Okay, that looks somewhat new. What I mean to say new is, you should remember the definition for the Laplace transform of f of t. Let me write down here. This expression is nothing but integral 0 to infinity. You must have e to the power of minus st ft dt. Okay, this is the one that is definition. So we remember this is the one that we got now. So we are going to compare. So keep one hand here and keep this one here. You compare this. Dt is there, f of t is there, f of t is there. But then here e to the power minus t s minus a is there. This is e to the power of minus t s is there. So t s is there, t s minus a is there. So looks like little something is there. So for that reason, let us rename this s minus a as a new variable s prime. So that the minus a will not be visible to you. Or equivalently, we are going to another graph which has been shifted. Okay, we have a graph paper which has been shifted, moved. That's what is the meaning. So that is equal to integral 0 to infinity. We get e to the power of minus s prime and then you have a t, then you have f of t, then you have a dt. So that is the value of the integral that you have. And now if you compare these two, you are comfortable. This one you compare with this. The only difference is here s is there, here s prime is there. So quickly you can therefore write down that this is nothing but capital F of s prime. Okay, that is why I told that this is the one that you have to remember. Whenever there is a L of f of t, the answer is capital F of s. If you are going to have s prime rather than s here, then here also you have to change s to s prime. So ultimately we got the answer. Answer to what? Answer to this problem. Laplace transform of e to the power of 80 into f of t is given by f of s prime. But however, what is s prime? Again you have to read here. So where s prime is nothing but it is actually s minus a. So now you write down that this is s minus a. And let us write down this one for the conclusion. So we write like this: Laplace transform of e to the power of at, a function of t. Okay, so what you understand from here is that I am going to start with a function which is f of t, and then I am getting the transformed function which is shifted by an amount a to the right side. Okay, that's a minus a means shifting happens to the right side of the graph paper. If there is a plus here, shifting happens to the left side of the graph paper. So that means if I am going to draw like that, this is 0. If I am going to move like this and put a dot here, that is s minus a. If I am going to come to the left side and put a graph like that, this is s plus a. So that is how the shifting takes place. Shifting is not on the horizontal, it's on vertical. Okay, because we are talking about the real part, right? So that is the place where a happens. Real part of a is here. Real part of minus a is there. That is minus a. So this is the final conclusion. This conclusion is very important. And now I would like to rewrite the same thing in a slightly different way so that you can easily work out when you are doing the example problem. Okay, so the initial steps I will erase. This one we are going to rewrite little bit so that it is easy to understand. So what all is this equation that we have written? Let me write down one here. So one is nothing but, equation 1 is nothing but, it is identically same as, we say like this: Laplace transform of e to the power of at into f of t is nothing but f of s minus a. How do you understand this? It is originally f of s, like that you understand, because we are always comfortable with f of s. F of s minus a means nothing great, but however initially there will be some confusion. So you first find out what is f of s, then you replace all s by s minus a. So how you understand this is, for practical calculations, you first find f of s as usual, then replace. What is the meaning of this is, replace every s by s minus a. Simply replacement. If you do that, that is called f of s minus a. Okay, so that's what you mean, you understand, capital F of s minus a. So this line, this is the very important for understanding purpose. Based on this, you can do the problems and then get the answer by doing this replacement. Replacement is easy rather than writing down f of s minus a. That's all about it. And now we will take an example and see how we can apply this rule. So the question is like this: 4t. So that is the question. So as you can see that cos 4t, you can quickly find out the answer. Then you will be thinking what to do with e to the power of minus 2t, and that is exactly this function that you have. Okay, so you have the multiplication. Whenever you have this problem, this e to the power at, you just, it is coming only for, this is the portion which comes for replacement. So e to the power at, you simply forget. You simply forget in the calculation. Only take f of t and do the calculation, and after finishing the calculation, because of the a here, you replace by s minus a, you get the answer. So that's what we do. Let us do the, what is the solution is that, let us say that the answer is, this is given by, we can say that this is given by the Laplace transformation of cos 4t. That's all over. We finished the answer, in which you replace every instance of s by, so what are you going to replace by? There's a minus 2 there, therefore you have to put s plus 2. So every instance of s has to be replaced by s plus 2. There is a plus 2 is coming here because there is a minus 2 minus 2 is there. So that's all about it, and we know the answer because you know this result already. So which means that this is equal to s divided by s square plus omega square, in which you replace s by s plus 2. Okay, so that we can simplify maybe here. Let us replace this s plus 2 by s plus 2 whole square plus omega square. Of course, here, I have written omega here. Actually, this is a 4t, right? So omega square is nothing but 4 square. So better to write that. So in that way, this becomes actually 4 square here, which is 16. So that is equal to, you can simply expand this and write down s square plus 2s plus 20. So this is the answer. So your job is only the replacement. The rest of the thing is, it is optional. Whether you want to simplify like that or leave it like that, both are okay. But you now see that the effect of the e to the power minus 2t, okay, the effect of the e to the power minus 2t did not give any trouble for your integration because it happens to be a shifting property. This is called a shifting property. Okay, either you can call it by the name S shifting theorem, or you can call it by the name S shifting property. You can ask the question, if this is a circular function, if this happens to be hyperbolic function, then there is no much change. You can easily see that this is, suppose what happens if it is hyperbolic function of omega t, then the changes are very little. You just modify this to minus. So with that you get the answer. So therefore, if this is a hyperbolic cos, suppose if this were a hyperbolic cos like that, then you only have to put a minus. So that means I have to put a minus here. So this is the place where you put minus, that corresponding to the hyperbolic function. So therefore, when I am putting the hyperbolic function here, hyperbolic of 4t, when I do that, put a minus here, and that's all. So when you simplify this, I will not get plus line. So minus 16 supposed to be minus 12. That's all. That is the answer. So many of the problems wherever you can manipulate with the expressions for e to the power of at, all result is coming from this one, and therefore we started with this as an example in the previous class. So once you know this gamma function clearly, Laplace transform will become comfortable for you. Okay, we will meet again in the next class with another property. Okay, bye.